Hey guys, it's Max, and we're back with Battlecode 2015. This time, let's look at various ways to path around the map. We're going to do this in Mathematica because it's a little more visual. This is a program that makes a random maze, which we'll use for testing the map. You can see it makes some random walks, and it gives you this nice looking maze. Our goal will be to get from the bottom left to the top right in various different ways. Here's one way to do it, using depth first search. I'll set a delay in here so that you can see it as it's pathing. So it starts in the bottom corner and it's searching along the maze. In depth first search, it's going to pursue deep avenues before it pursues shallow ones. So this turn here to the left, it didn't look down there because that's a shallow avenue. It only stops when it sees a dead end and then goes back to the latest point where there was a choice. So here it's going to move and it sees a dead end, so then it went back to here. And now it's checking the left. One feature of depth first search is that it doesn't know for a fact that it's found the shortest route when it finds the target. It has to keep looking. See, it checked over here because this one might have led there faster. This is in contrast to breadth first search, which looks like this. Here we can see that it's pursuing and extending all the paths in parallel. One feature is that it knows that when it's found the target, that's the closest path. Breadth first search is a good choice in my opinion. I think it's always better, but somebody else might be able to prove me wrong. The difference is simply in which order you process the ends of the paths. In breadth first search, you process each of them sequentially. You can read more about this online. I just think these look cool. Let's look at another option. A lot of people know that in a maze, if you stick your hand out and keep it on one wall, say keep your right hand on the wall, then you'll be able to find the exit just by following the wall. That's got something to do with topology. And that's what we're going to see in this bugging example. So bug pathing is not quite the same as keeping your hand on the right wall. The way it works is you'll follow a wall until the wall ends, and then you'll start to go straight toward your target. Let's see that. So the yellow dot in this example shows his hand on the wall. And we see that there's a lot of backtracking involved in following this method. Here, he turned around because he had left following the wall and there was a dead end in front of him, and he has a preference for turning left. So in the end, this means that there's going to be a whole lot of backtracking that takes place, and if you just watch this, it might seem like he's never going to find the solution. I'll pause the simulation and make it a little faster so that we don't have to wait through the whole thing. Okay, I'll set the delay to 0 so that it will execute as fast as possible. Okay, so he did find the solution after some time. Let's change to a different map and see how things look when things are a little more open. So here's an open map. We're going to start again at the bottom left and go to the top right. Let's use depth first search. This is a little bit slow. Let's try making it a little faster. Oh, and what's he doing? Some weird kind of back and forth motion. Let's see what this looks like when we go a little faster. Okay, so he goes up and he's trying this long and convoluted path. It seems like it makes no sense at all. And this is the nature of depth first search in a wide open terrain, is it's trying a bunch of pretty much redundant paths. I mean, it makes no sense to get to your destination and then keep going and check all these other paths, but it makes no assumptions about the relative distances from different tiles to one another. And for all it knows, from going from this tile to that one in just this specific way could be a shorter path. I guess this makes sense if your system is somehow non-uniform, but in Battlecode all the distances are uniform, so let's go ahead and pause this so we don't have to wait all year for it. Let's see here. I'm just looking for the abort key. Okay. Now let's try the same map with breadth first search. So we can see that it's searching all the directions around itself and extending things uniformly. There's a lot less duplication of effort here, and I think it's pretty clear that it's going to get to this solution a lot faster. Right now I've got a delay of 0.1, so it's not instantaneous. But if we set the delay a little smaller, like to 0, then we'll see it reach the destination really pretty quick, even on this slow laptop, and even with all this graphical plotting. So it finds the destination, and that's a pretty good looking path. Lastly, let's see what Bug does on the same map. Okay. So he hits the wall, and he follows it until he sees the wall has ended. Then he goes straight toward the target, but he ends up hitting this wall, and he has to follow all the way around until he gets closer than here, and then he leaves the wall and finds the target. It's a little bit convoluted, this path. Definitely not the fastest way. However, there are some changes you can make to improve the bug pathing. I mean, the good thing is that in bug pathing, it takes very little computational power, and that's important in Battlecode. If you do have some computation power to spare, you can try to modify the path to improve it. And I'm going to do that with post-processing. So I'll say that the unit has imagined this path ahead of time, but not actually taken the path yet. Here's a schematic of how it's going to try to improve the path. On the first turn, it notices that it's going to be turning left, which is shown in red. All the left turns are in red and the right turns are in blue. It notices that it's going to be turning left, so it tries to make that turn early. So it's currently located at this red circle, and it's checking the tile indicated by the green circle. And if that circle is available, it'll turn early. Same thing if it's here. If it's going to be making a right, it'll try to make that right turn a little earlier. And so on for the entire path. Let's just fix that. So on for the entire... just got to fix this here. Okay, so for the entire path, it'll be trying to make the turns earlier than they actually appear. In this case, it can't make the turn any earlier because there's an obstacle in the way, so it can't make that right turn until it reaches here. Okay, so now let's see how that path looks and see how it changes when we try to make those turns sooner and try to simplify the path. Okay, so after one simplifying step, we see that it doesn't actually get so close to this wall. It turns a little sooner. Same thing before it hits this wall and the other wall and the other wall. And we can keep repeating this step to improve the path even more. In some places, the path doubles back on itself, and in those cases, it will delete the duplicate path, because there's definitely no point going somewhere and coming back along the same path. And so we repeat this step, and we see that loops close into lines, and the lines ultimately will retract because they consist of duplicate paths. So we'll keep going, and we see these lines getting simpler and retracting. And ultimately, after a few more steps, we come to basically the same path as the correct solution. So this is a powerful way to modify a simple code to get to a much better solution. This is mostly meant to inspire you how to do these kinds of things, and not to actually be a direct implementation explanation. Lastly, I'd like to consider the case that we've got more than one unit. See, before we were just talking about getting one unit from place to place, but in reality you may want all of your robots to converge on a central location. Here I've made a map test where we can import a map, and I've imported this map that's shown here. Let's assume that all of my robots want to get to this point here, this headquarters from the enemy. One way to do that is to fill colors going outward, and those colors represent directions. So it's a flood fill direction finder for every tile. I'll show you what that looks like. So starting at that headquarters, we're going to fill colors radiating outward, and each color represents a direction. When it encounters a turn, the direction of the fill is then painted as the color. So let's interpret this diagram. Red means go up, because that means you would reach the headquarters if you were going up. And purple means go up and to the right. Pink means go to the right, and so on. So if we pick a random tile, such as here, red means go up. So if I'm a robot located here, then I should go up, and then I'll hit purple. Purple means go up and to the right, so then I go up and to the right, and then I hit orange. Orange means go up and to the left, so then I'll go up and to the left. Maybe I hit this purple, go up and to the right, orange again, up and to the left, red, and then I go straight. And so this has managed to navigate me around obstacles to get to the enemy headquarters in a pretty effective way. What's cool about this technique is that it works on just about any map, and you can actually compute this with all of your robots together. They can work together to fill this in, because after all, each step is just dependent on what the last step was. There's no other information stored. You might be wondering, how can I make this work in Battlecode where robots are not given full knowledge ahead of time what the map looks like? Well, it's not too hard, because any terrain that your robot has seen, any terrain that any robot on your team has seen, will be stored in memory, and you can access that memory with rc.senseTerrainTile. So that means that by the time 1,000 rounds have passed, you probably have a good idea what the map looks like. The headquarters or some other unit can generate a map like this, post it to the message array, and then your whole team can use it. It's especially useful on a map like Trenches, which is very hard to navigate. So let's look at that one. 1, 2, 3, 4, 5, 6, 7. So I'm going to look at map 7, which is Trenches, and let's say we're going to try to get to this headquarters here. Okay, so we see it filling out from there again, and especially on this map, there's a lot of turns necessary to get to that location from somewhere else. I've got it with a delay of 0.2 between each step, but that's just for plotting purposes, just to make it easier to see how it fills. I think this looks really cool. It's kind of psychedelic. Let's follow the example again, supposing we're here. Yellow means move to the left, because it's to the left of this headquarters. So we move to the left. Orange means move up and to the right. Red means move up and to the left. Green means down and left. Teal means down and left. Orange means up and left. Red means down. Red means up, so we go up. Purple means up and to the right, and you can see that we're gradually getting toward the enemy, despite the complexity of this terrain. Up and to the left, left, up and to the left, up and to the right, up, and so on. And we're going to get to the enemy headquarters. This is really powerful, and it means that each robot needs to use only a few bytecodes. He just needs to read a message that says which direction he should go on his tile. You can fill the message array with this information pretty easily, because the message array is 65,000, and the map is going to be no larger than, at most, I don't know, 60 by 60. So you can simply put these numbers in, 0 through 7, to represent directions, and then each robot just reads the direction it needs to go to, directly from its position. You can index the positions relative to your headquarter positions if you need to use something like that. So this method's pretty easy to implement, and I'm pretty sure you can figure it out. And I hope this gives you some ideas about clever ways to path around the map and get your robots where they need to go. Hope this helps. Bye-bye.